Wind turbines are remarkable feats of engineering, clean energy machines built to withstand high winds, harsh climates, and thousands of hours of uninterrupted motion. But among all their moving parts, the blades are the most exposed, most vital, and most vulnerable components. Towering hundreds of feet in the air, these aerodynamic structures battle rain, hail, lightning, and microscopic airborne particles that erode them over time. Even the most advanced turbines are not immune to damage, and when the blades fail or wear down, power production drops, efficiency suffers, and risks multiply. This is where blade repair technicians step in. They're not just climbers or engineers, they're artists of composite repair, surgeons of fiberglass, and acrobats suspended in the sky. This article explores everything from common blade damages and repair processes to gear checklists and field-tested techniques. Designed for both seasoned professionals and newcomers, eager to understand what it takes to keep turbine blades spinning strong. Understanding blade damage, types and troubleshooting methods. A turbine blade isn't a simple piece of fiberglass. It's a precision-engineered aerodynamic structure built from composite materials, typically a mix of fiberglass, epoxy resin, balsa wood, and carbon fiber. These materials are lightweight yet strong, but they're also prone to specific types of wear and damage, often triggered by environmental exposure or mechanical stress. One of the most frequent issues technicians face is leading edge erosion, LEE. This form of damage occurs when tiny particles like sand, rain, and hail slam into the blade's front edge at high velocity. Over time, this causes pitting and roughness that disrupt airflow, reducing aerodynamic performance and turbine output. Left untreated, the damage grows deeper, eventually exposing composite layers and leading to delamination. Another serious issue is lightning strikes. While blades are built with internal lightning protection systems, usually metal conductors running down their length, a direct strike can still burn through the gel coat, create holes, and sometimes even cause internal delamination. Damage isn't always obvious. That's why ultrasound and thermography tools are essential for detection. Cracks and splits are another headache. These can originate from manufacturing defects, material fatigue, or extreme wind loads. Cracks often appear as hairline fractures near the trailing edge or as longer splits running parallel to the blade's length. Proper identification involves visual inspection, tap testing, and in many cases, stop drilling to prevent crack propagation. Then there's delamination, which refers to the separation of layers within the composite material. It often starts subtly and can be invisible to the naked eye. You might detect it only by hearing a dull, hollow sound during tap testing. And finally, bond line failures, particularly along the trailing edge, can compromise the structural integrity of the entire blade. This is when adhesives fail, causing sections of the blade to vibrate, loosen, or even peel apart mid-operation. In all cases, technicians must determine not just the type of damage, but its depth, location, and potential impact. A simple surface nick might require a cosmetic patch, while deep-seated internal damage could demand a full structural rebuild. The blade repair process: scarfing, bonding, filling, and finishing. Once damage has been identified and mapped, the real work begins. Repairs can happen in blade manufacturing plants, repair hangars, or, more commonly, on-site while suspended 300 feet in the air. Regardless of the setting, the process follows a meticulous, step-by-step procedure. The first step is always assessment and preparation. The technician marks the repair zone clearly, often including a blend-out area that extends beyond the visible damage. Tools like tap hammers, moisture meters, and thermal cameras help confirm the extent of internal delamination or water ingress. Next comes scarfing, one of the most critical and technical parts of any blade repair. Scarfing involves grinding or tapering the damaged area into a beveled surface. This is done to create an extended bonding area where new fiberglass layers can be applied, ensuring maximum strength and smooth aerodynamic restoration. The grinding is typically done in a controlled spiral or elliptical pattern, using ratios like 1:20 or 1:30, meaning the taper should be 20 to 30 times longer than the depth. Dust extraction systems and respirators are essential here. as grinding composite materials releases hazardous particles. Once scarfing is complete, the area must be thoroughly cleaned, often multiple times using acetone or blade-specific cleaning agents. Any residual dust, moisture, or oils can compromise the adhesive bond. With the surface prepped, technicians begin the lamination and bonding process. This involves layering cut-to-size fiberglass or carbon fiber cloth into the scarfed area, saturating each piece with epoxy resin, and carefully stacking them to match the original laminate's strength and direction. If the damage involves structural cracks or bond line failures, special high-strength adhesives are used to rebond separated components before laminating. In some cases, vacuum bagging techniques are employed to compress the repair area, remove air bubbles, and ensure flawless adhesion. After bonding, the technician uses filler compounds to level out any depressions or inconsistencies. These are lightweight, sandable materials designed to restore the blade's aerodynamic contour. Once cured, the area is shaped using orbital sanders and grit paper in a range of fineness until the surface is perfectly flush. Finally comes the top coat and finishing stage. This is where technicians apply UV-resistant paint, protective coatings, or leading-edge protection LEP tapes. These materials not only protect the repair, but also reduce future erosion and help maintain airflow over the blade. Each repair concludes with a rigorous quality control inspection. This includes a checklist of materials used, curing times, environmental conditions, and before and after photos. Non-destructive testing may be used again to confirm bond strength and internal integrity. Inside a blade technician's toolkit, what's really in the backpack? Climbing a wind turbine isn't like stepping onto a rooftop. It's a high-stakes, high-altitude operation that requires a carefully curated set of tools, materials, and safety systems. Every item in a blade technician's backpack is there for a reason. Nothing extra, nothing missing. At the top of the list is personal protective equipment, PPE. This includes a full-body rope access harness, helmet with chin strap, cut-resistant gloves, safety goggles, and a dust mask or respirator. When grinding fiberglass or applying epoxy resins, respiratory protection is non-negotiable. Next is the technician's rope access system. A typical setup includes 2 static ropes, 1 working line, 1 backup, a descender like the Petzl ID or CT Sparrow, a handle descender for climbing, and a fall arrest backup device such as the Petzl ASAP. Carabiners, lanyards, slings, and anchor systems round out the climbing essentials, and each component must be inspected and certified before use. In terms of repair tools, the tech will carry a cordless grinder with dust extraction for scarfing, an orbital sander for smoothing surfaces, and a tap hammer for damage detection. For bonding and filling, the bag includes measuring cups, mixing sticks, rollers, and brushes. It may also contain vacuum bagging materials like sealant tape, peel ply, breather fabric, and vacuum film. A compact vacuum pump and temperature gun help control curing conditions in the field. No repair can proceed without the actual composite materials: spools of fiberglass or carbon fiber cloth, 2-part epoxy resins, adhesive cartridges, and filler compounds. Each material must match OEM specifications exactly, as using the wrong resin or fiber orientation could jeopardize the blade's structural integrity. Technicians also carry coating systems, whether spray on LEP, brush on UV paint, or leading-edge protection film. These are often field-approved products specifically. Pro tip: a seasoned blade tech will always carry a just-in-case pouch with extra gloves, small first aid kit, weatherproof notebook, zip ties, duct tape, and spare fasteners. Final thoughts: the precision art of blade repairs. Blade repair isn't just about fixing fiberglass. It's a specialized craft that balances aerospace-grade precision with industrial grit. At the tip of a wind turbine, exposed to wind, rain, and vertigo-inducing heights, technicians perform intricate composite repairs that restore aerodynamic performance, improve energy yield, and extend the life of million-dollar assets. From scarfing and bonding to UV sealing and structural reinforcement, every step must be executed with military precision. Every grinder stroke is calculated, every resin mix is documented, And every ascent up the tower is backed by a redundant safety system and rigorous training. The next time you look up at a wind turbine and see its blades spinning silently, know this: behind that graceful motion is a team of rope-hanging warriors, hauling grinders and epoxy, one backpack toolkit at a time. Want more content like this? Stick around for upcoming tutorials, behind-the-scenes repair walkthroughs, gear reviews, and rescue simulations from the front lines of turbine maintenance.